Test 1, 2.
All right, good evening, everyone. First of all, thank you for coming out to see us even in this really bad weather. I'm Viola Simwanza. I'm the president of the American Chemical Society student chapter. And today we'll be doing our chemistry magic show. So we've got a whole lot of fun demonstrations for you guys, and you get to see how cool chemistry is and much more interesting than engineering. So I'll let them introduce themselves.
Hi, I'm Sierra. I am our PR person for the ACS Club, and I am a junior.
Hi, I'm Tanya Martinez. I am a freshman and I am a member of ACS.
I'm Taylor Schramm. I'm also a freshman and I'm a new member.
My name's Philip Hauk. I am a master's student studying chemistry, and I've done just about every position of this club in the past, so been here for too long.
I'm Connor. I am a senior chemistry student, and I've also been in pretty much all the positions. And like Phil, been here for just a little while.
All right, so we're going to kick it off with our first experiment. Who is that? Which is our sodium polyacrylate demonstration.
Who here has heard of what a polymer is? Maybe you're more familiar with a plastic. It's a very common example of a polymer. So we're going to give a quick little intro into what a polymer is, and then we're going to play a game. So a polymer in chemistry is essentially a chain of monomers, which doesn't make a lot of sense. A monomer you can think of as a group of atoms bonded together in a very specific pattern. So here's an example called sodium polyacrylate. This is going to be our sodium polyacrylate monomer. And when you kind of string them all together, you create this polymer of sodium polyacrylate. And you can kind of think of this like a Christmas tree lights, where you kind of have each light bulb as your group of your group of atoms, and they're all kind of strung together in a long chain. There's a lot of different polymers. There's synthetic and natural polymers. Most synthetic ones you're probably familiar with are like your 6 common plastics, so like polyethylene, for example. But some other common natural polymers are, say, like cellulose and like wood or vegetables or anything you eat. There's thousands of different polymers. They have a ton of different uses. And we're going to play a game having one type of polymer. So I'll give this to Connor. Okay.
That one.
So we're going to pour water into one of these cups. And then we're going to mix these around, and I'm going to have you guess what cup the water's in, okay? So keep an eye on. All right, who thinks the water's in this cup? Nobody? Okay. What about this one? Okay. How about this one? You guys think the water's in this one? All right. What about this last one? Where'd the water go? It did stay in the cup. So what we had hidden in our bottom of our cup here was a polymer called sodium polyacrylate. This polymer is very good at absorbing water. It can hold up to like a few hundred times its volume in water. You're probably most familiar with this is what they put in baby diapers to help absorb liquids. You can also use it for like fake snow on movie sets. Also as like an additive for plant soil to help retain water. A lot of cool common uses for this really interesting polymer. It kind of makes like a little gel. So, any questions? And we'll go on to our next.
Our next experiment, I believe, is elephant's toothpaste. Who's heard of elephant's toothpaste? Al? All right, we'll pass it on to Sierra and Viola.
All right, so me and Sarah are going to do the elephant's toothpaste demonstration. So first I'm going to start by adding, will you hold this?
Yes.
A bit of hydrogen peroxide, which you guys probably have at your houses. It's a very good antiseptic. A lot? Or a little more? A little more. All right. And I'm going to add some dish soap. A lot? I don't know how well you can see.
Say one.
Is that enough? Okay. I will let you guys pick the color though. We have blue, yellow, and red. What are we feeling? Yellow? Blue? Let's see. Chartreuse is green. I'll add a little bit of yellow. We'll make green. All right. And now, I'm sure some of you guys have probably seen this. It's a pretty popular demonstration. But what do we think is going to happen when I add some saturated potassium iodide? Let's see.
Oh no, it's in
So-
your hair. All over you. Oh, dude, you're stained.
Oh, this is my first time doing this. I probably won't be allowed to do it again.
Success.
So, does anybody know what happened? So, like I said, hydrogen peroxide is something you're probably familiar with. You might have some at your house. If you have a wound, it's something you could put on, you see it start to bubble up. But it actually likes to undergo this reaction where it breaks down into water and oxygen. That's why we keep it in dark bottles, because light can speed up this reaction. So over time, you might find that when you go to put it on a wound, it's not working as well as it should. And so by adding the potassium iodide, it works as a catalyst. Catalysts are just things that we add to speed up a reaction. So instead of breaking down over the course of days, we saw it break down really quickly in seconds. So yeah, I'm so sorry to whatever janitor. All right, I think we're ready for the next one. Sierra? Next slide, please. There we go.
Right. Hello, everybody. So tonight we have some cool magic beakers that we're going to show you guys. So can everybody see these beakers right here? All right, perfect. So we're going to do some cool tricks with these magic beakers. So in this first beaker, this one's not magic. This is just a normal beaker. It has water in it. So we're going to start by pouring the water into this beaker. Does anybody know, do they think anything's going to happen? All right, let's go for it. Looks like just plain water to me still. So we're going to go to the next beaker. We'll see if this one's magic. Whoa. Okay, guys, do we think the next one's magic? All right. Looks like it's the same to me. All right. And our last beaker? Where'd all the magic go? All right, I'm gonna let you guys in on a secret. These are not magic beakers. Okay, so what we started out with was actually just normal water. I was not lying to you about that one. But in all of these other beakers, so the first one, we had a little bit of sodium hydroxide in it. So the sodium hydroxide started to react with the water, but it stayed clear. It didn't have a color change reaction. But when we put it into the next beaker, which had phenolphthalein in it, the phenolphthalein reacted with the sodium hydroxide and the water together and made a pink color. This beaker actually had nothing in it, so we weren't lying to you about that one. But when we put it back in here, this one had acetic acid in it, which reversed the color change and made it clear again. So acetic acid, does anybody know what acetic acid is in everyday, like, cooking? So it's actually vinegar. So this last beaker just had normal vinegar in it. So this was just one big chemical reaction that changed color and then just changed back because the reaction got reversed back to just the clear color. So yeah, pretty cool. I don't know what's next. I think it's cabbage. Ready for cabbage? All right.
Hello, everybody. Here. So next is our red cabbage juice experiment. And we are doing another thing with pH, similar to what the previous girls just did. You can see here, this is our pH scale based off of cabbage water. So based off of how acidic or basic something is, we can get all of these different colors from different products. So here in this flask, we have some of our lovely cabbage water. You can see it's a very dark blue color. And we are going to pour it into numerous different things and see what colors they change. Okay, our first one we have here is Coke. And we all kind of know, dentists say Coke is bad to drink because it's acidic and it rots away your enamel in your teeth. So what color do you guys think this one will turn? This end is more acidic and down there is more basic. You can shout it out. Red. You want to pour it in? You can, I would hold it up. Yeah, hold up the beakers so they can see. Okay. Oh, just a little bit. Yeah, we can kind of see. It's hard to tell with the Coke, but it did turn a more of a reddish pinkish color right in here. So that does show us that it is more acidic. Next, we have baking soda. Does anybody know what baking soda is? Yeah? Something you use to make cookies? Well, what color do you think this one will turn? Good guess. Let's see. And you were right on. It's more of a lightish blue, right in this 8 range. Our next one we have is vinegar. Vinegar is acetic acid, so we can kind of guess what color that'll give us. What one do you think? Red. Oh, right on the money. We got a hot pink, right in about 3, 2. Next, we have our favorite Dawn dish soap. What color do you think? Purple? Kind of a darker blue. So we're more at like a 7, so very close. Which means it's kind of neutral. Our next one we have is ammonia. It's a common cleaning agent. I'm sure you've all smelled it. What color do we think? Green? That's a good guess. Oh yeah, look at that green change. That's very, very basic. Okay, our next one, Head and Shoulder shampoo. We all use shampoo. What color? Purple. That was a really great guess. We do have a purple one. Our next one, hand sanitizer, something we all use and are very familiar with. What color? We have a bluish purple. So about 6. Okay, our next one, lemon juice. What do we think? Basic or acidic? Acidic? Okay, let's see. And we have oddish pinkish, about 2. Our last one is this mold remover. It's a cleaner. What color do we think? Yellow. Oh, we have a bluish green. So that shows it's about an 11. Okay. The reason why cabbage water has this ability is it has a compound called anthocyanins. They're actually what makes the cabbage its purple color. And it can change into all of these different colors based off of the pH or the acidity or basicity of the compounds that it reacts with. And these anthocyanins are actually antioxidants. So red cabbage is actually very good for you. And you can do this kind of thing at home with your own food. And you can play around with it. It's really fun to do. And I highly recommend it. And it's good for you. Yeah, I think that sums up our experiment.
All right, so who knows how traffic lights work? How do they work? Pull up in red. All right, so I have a traffic light, but it's a little different. So for this one, I've got some sugar water and indigo carmide. And indigo carmide is just another one of the pH indicators, or just a little dye. And then in here, I got some sodium hydroxide. So what do you guys think will happen when I add the sodium hydroxide? Anyone? I'll give you a hint. All right, so I add the sodium hydroxide, which is still a little dark for you guys. I don't know if you're able to, are you guys able to see the color? Or I'll add a little water to dilute it down. Maybe. All right, so it's kind of hard to tell for this one, but it's currently a green. And if we let it sit here, so we're at green, and it's kind of turning blue right now, because it's going to be switching over to the red, if I can get it. So when we shake it, we get green. I'll let it sit for a little while. We get the green. And then it will go over to the red and then go over to the yellow. And then we shake it again and it will go back fast. So what we're doing when I'm shaking it is I'm adding oxygen to the liquid, and then it's an oxidation reduction reaction. And when I add the oxygen, it changes the color, changes these, and returns into a green. This is real dark. I added water. Yeah. Do we don't have a flashlight. So, and then while we do it, while we go through it, that doesn't help at all, does it? Yeah. So we need less indigo carbide next time, Filipova. But so if we had less of the indigo carmide, it would be a nice green, and then it just switches over to the red, yellow, and then we shake it again, and it will go back to the green. But with how dark it is, no, yeah, so now we know for next time, don't add as much of the indigo carmide, but it will, yeah. While we're sitting here, it will also, as it reacts, it will get less and less strong of a color, hopefully. All right, next slide. All right, Phil, if you would like to come on out. All right, so our next experiment involves some fire. You want to do it down there?
Put it on like fire. Yeah, and then would it be possible for to get the lights here away from the?
Yes, please.
Who here likes fireworks? I do. Have you ever wondered on the 4th of July why certain fireworks are different colors? No? I have. The real reason why fireworks are different colors is because they have different heavy metals in them. Each heavy metal releases a specific wavelength or color of light when it gets excited. That essentially means whenever you add energy, for example, heat, to solutions with metals, the electrons orbiting the center nucleus of the atom will get excited and they'll gain a bunch of energy. After a certain period of time, those electrons will lose that energy and they'll emit a photon of light. The amount of energy that's released by that photon determines what color it is. So here we have a few different solutions with different metals, and we're going to hold them into a flame, and we're going to have you guys guess what colors they are. Okay. So up first we have calcium. What color do you guys think it's gonna turn? Green? We'll see. Over here more. You guys see it's kind of this nice little red orangish color. All right. Up next we have copper. What color do you guys think? What color? Green? Okay. Up next we have potassium. What color do you think? Blue? We'll see. The blue and the red are from the propane torch and the wood burning, but it's a white flame. All right, up next we have lithium. It's gonna be another red color. You guys see it? All right, and last up we got lead. What color do you think lead will be? Yellow? Kind of this orangish flame with a little purple undertone. Okay. That's all we got for our flame. Now you guys know how fire works.
All right, so as we're heating it up with the fire, the electrons are getting excited. So the fire is our heat or our energy source, right? How else do you think we can add energy to things? Anyone? Light? So do you guys, all right, black lights or ultraviolet lights? Next slide, please. So ultraviolet lights also can do, back one. All right. So the ultraviolet light will also do this, but this one is called fluorescence. And so when you shine a black light or ultraviolet light on certain things, they'll absorb it and then cause the electrons to get more energy. And then when they fall back down, that's what you see. Like when you shine, here, I'll turn this on now. So like for the white, it becomes the blue or, yeah. So next screen now, please. All right. So like our lab coats, we got white lab coats, right? Now they're all blue, or we've got, so we got a uranium glass, which glows a nice, pretty green. We've got a little sign with a bunch of different inks on it. What else do you guys think can glow like this? Can I glow? Do you think I can glow? So is my arm glowing? What if we go like this? Does this arm glow? So are you guys able to see that? So some tattoo inks also glow in the dark or glow under a black light. Some other things like driver's license will have security features on them where they have different things show up under UV light, or like the $100 bill has a little thing on it. Yeah. So next slide, I believe is bubble.
Get the lights back on, please.
All right.
Okay. Who here has heard of dry ice? Who here knows what dry ice is made out of? You can shout it out. It's made out of carbon dioxide. Good job. Who here knows what carbon dioxide is? It is what you breathe out. So you breathe in oxygen and then your body converts it into carbon dioxide and you exhale. So the reason why it's called dry ice is because it's frozen carbon dioxide, meaning there's no water in it. One very unique property of dry ice is that it undergoes a physical change called sublimation, where it goes directly from a solid into a gas. So typically, if you know you have solid ice or solid water, it's called ice. And then you melt it, it becomes water, and then you keep heating it up, and then it boils and becomes steam. Here we're skipping that liquid step, and we're going directly from that solid to a gas. So in my little container here, I have some dry ice. We'll add some to our water. The water here just helps speed up the phase change going from solid to a gas. And so you can see here it's going pretty good. We're gonna stick this in here. All right. What do you think? What do you think will happen if I add some soap to it? Make some bubbles. Give this a mix. All right. The cool thing about these bubbles is that they have the solid carbon dioxide or the carbon dioxide trapped inside. So if you give them a squeeze, they'll make snow. And this will just keep going here until either all of our dry ice gets sublimated or eventually a layer of frozen water will form around our dry ice because it's so cold. Does anybody know how cold dry ice is? Really cold. I actually forgot the exact number. I believe it's like negative 100 and what is it? Negative 109 Fahrenheit. I was gonna say 100. That was pretty close. So very, very cold. Even much colder than it is outside. So that's the reason why I have to wear these special protective gloves so I don't get frostbite. So, any questions about dry ice or sublimation? All right. Then we'll go on to our next experiment.
All right, so my favorite experiment, get it all up here quickly. You're fine. So this one, I'm gonna be having some flowers. I got a racquetball. I've got some balloons and a hammer. So does anyone have any idea what is in my little bucket here? Liquid nitrogen. So Phil said the dry ice was negative 109 Fahrenheit, right?
Yep.
Anyone know what the temperature of this is? Close. Negative 321 degrees Fahrenheit. So dry ice, that's cold. Outside is cold right now. This is a lot colder. So what happens when you make things cold? Like when you get a rubber band cold or any rubber cold, what happens? Does it, yeah. So it doesn't stretch as well, right? So I got a racquetball here. It bounces nice and well. Phil, would you like to bounce your racquetball?
Here we have a racquetball that we have been cooling in liquid nitrogen. What do you think will happen when I drop it? We'll see.
Did that sound a little different? So this one, the racquetball loses its elasticity. So like it can't stretch as much anymore compared to this one that can stretch nice and a lot. What do you think happens if I put flowers in the liquid nitrogen? They're gonna shatter. Throw them on the ground. So, the flowers. I can take the flowers and I can smack them on the table, right? Nothing happens. So if I stick them in here, I'm gonna grab my racquetball, set my racquetball right here. Then I'm gonna take my flowers back out. They shatter, and now there's no more flower. So the same thing's happening with the flowers. They're losing their elasticity and they can't stretch. Now, should I shove my hand in there? Yeah. What happens if I shove my hand in? Nothing happens. So, there's a fancy little thing that's happening. It's called the latent frost effect. And when I stick my hand in there, so what's the temperature of my body in Fahrenheit? 98 degrees Fahrenheit, right? So that's over 400-degree difference in temperature. So when I stick my hand in there, a little layer of air protects me. If I were to stick it in there, leave it in there, this would be my hand. But since you go fast, you just got a little bubble of air. Now, how many balloons do you think we can fit in here? One?
All right, we'll see.
All right, so this is one.
All right. Looks like we can get another one in.
Two. Any other guesses besides one? All of them? 6 of them? Yeah. So, do you guys know what's happening with these balloons? What's happening? They're freezing? They're not quite freezing. They're shrinking. Why are they shrinking? There. So, yeah. All right. So, when you take air and heat it up or cool it down, it changes pressure, or in this case, it changes size. So, if you increase the temperature, it will rise like a hot air balloon. If you decrease the temperature, you take a balloon like this one, it's going to fall, but it's a little slow. If we used helium, well, we wouldn't be able to freeze it or make the helium get cold enough. But it shrinks. So if we take one of these out, so that kind of slowly floats down. Those fall a little faster. There's 2 things. So you're getting it less dense, or this case, more dense, because you're shrinking all the molecules together, which creates less pressure, and it'll go down. When you heat it up, it rises. And then when you reheat it, the pressure increases again, just like with the hot air balloon. Now, who wants to see something that's really cool? Does anyone have an idea what I want to show you guys? It may involve that, which is a cannon. There should be. Or also known by us as our liquid nitrogen cannon. So if we take our liquid nitrogen, yeah, and then we have some hot water as well. My ball fell. So if we take some boiling water and pour it into the cannon, what happens when we pour the hot water into the cannon? Nothing. When we pour the liquid nitrogen into the cannon, then what happens? It all evaporates like almost instantly.
Seven, 6, 5, 4, 3, 2, 1.
Okay, that's our show.
Once again, thank you guys for coming. We're here for any questions if you have anything you're wondering about our experiments or just any other chemistry questions.
Turning red, and then so if we shake this, they'll darken back up to green. Eventually, if you let this sit probably for an hour, turn all the way. Like,
Are we?
here.
I usually do.
So, any questions right now? So, it's a oxidation of dust so we're adding the electron to it, we're going a different structure, chemical structure, and that chemical will make the light refract differently. So with this one, we go so when you add the electron, it's green, and then when it's losing its electron, it goes from green to red and then a little different order.
Free balloons.
Yeah.
You want a balloon?
Pick one.
Take a few. We've got a bunch of them.
Pick a balloon. You can come up here and grab it. We have red, green, purple, green.
We have some baby ones. Thank you. Yeah, thank you for coming.